Hello and welcome to Jeremy's IT Lab. In this video, we'll cover policy-based routing, PBR. As you know, routers normally route packets based on their destination IP address, selecting the most specific matching route. PBR lets you override that default behavior, so routers can forward packets based on their source IP address, port numbers, protocol, packet size, and more. In this video, we'll break down how PBR works and walk through a basic configuration example. Let's get started. First, let's think about traditional routing as you've already learned. Traditional routing, and by routing I mean packet forwarding, uses the destination IP address of packets to make forwarding decisions. The most specific route in the routing table is selected. Here's the simple network we'll use in this video. We have 4 routers and a firewall, all using OSPF to share routing information with each other. Using that information, each router calculates its best routes to each destination and builds its routing table. For this demonstration, we'll be looking at how packets travel from R1 on the left to R4 on the right. In this network, traffic from R1 to R4 at 10.4.4.4 will always use the path R1, R2, R3, and then R4. And why is that? It's because that route has the lowest OSPF cost, assuming all of these links have equal costs. The path via the firewall only serves as a backup if the R2, R3 link goes down. Let's look at how it works. R1 has received a packet from one of its connected LANs, destined for 10.4.4.4. R1 forwards it to R2, and now R2 has to make a choice. It has 2 valid paths, but which is chosen to forward the packet? Here's R2's routing table. Which is the most specific matching route? It's this one to 10.4.4.0 via R3. An alternate path via the firewall exists in OSPF, but because it has a higher cost, it isn't installed in the routing table. So R2 forwards the packet to R3, which forwards it to R4. To make packets destined for 10.4.4.4 pass through the firewall, we have a couple of options. Before I show them, think about what you would do, using what you know about traditional route selection. One option is to make the path via the firewall more desirable in OSPF. For example, you could increase the cost of the R2-R3 link, or decrease the cost of the R2 firewall link. I configured R2's G2 interface, connected to R3 with a cost of 10. And here is the result. Now the route via the firewall is installed in the routing table, instead of the route via R3, because the total OSPF cost via R3 is now higher. As a result, all packets to the 10.4.4.0/24 subnet will be forwarded via the firewall. Here's another option. You could configure a more specific static route on R2. First, I returned the interface's cost to the default. I then configured a /32 route to 10.4.4.4 with the firewall as the next hop. And here is R2's routing table now. With this configuration, because of the longest prefix match, only packets to 10.4.4.4 will be forwarded via the firewall. Both of these solutions work depending on what the requirements are. When it comes to traditional routing, this is about as far as you can go in controlling the path that packets take through the network. Either modify the cost of specific paths, or configure more specific routes to direct particular packets along a different path. In either case, each packet is still forwarded based on its destination IP address. So that's the extent of the control we have with traditional destination-based routing. Now let's look at a set of requirements for this network. First requirement. Packets from 10.1.0.0/24 must take the path via the firewall. Second, packets from 10.1.1.0/24 must be routed normally, so they'll take the path via R3 when being forwarded to 10.4.4.0/24. These might seem like simple requirements, but they can't be met with traditional destination-based routing. That's because traditional routing forwards packets based on a destination IP lookup, not the packet's source IP. And our requirements need us to differentiate between packets based on their source IP, the 10.1.0.0/24 subnet versus the 10.1.1.0/24 subnet. As you probably guessed, the solution to this problem is policy-based routing. We can use PBR to steer certain packets based on their source IP, overriding the normal destination-based forwarding decision. Now let's see how PBR works. PBR allows us to override the normal destination-based forwarding decision used by traditional routing. Instead of simply looking up the destination IP address in the routing table, the router checks the packet against a route map. And the route map can match specific traffic, for example based on source IP, and then specify how that traffic should be forwarded. Before we look at any details, let's look at the big picture. First, we have to define the target traffic using an ACL. This ACL defines which traffic should be policy routed. I'll use an ACL called PBR ACL. The second step is to define the policy. In other words, define how the target traffic should be forwarded. This is where we use a route map. Route maps use match and set statements. For the match statement of our route map, we use our ACL from step 1. This means that traffic that matches this ACL should be forwarded according to the instructions in the set statement. I'll say set next hop 172.16.22.1, the IP address of the firewall. Now our route map is complete, but it doesn't actually do anything until you apply it, which is step 3. In this example, I'll apply it to R2's G1 interface. The route map is applied to an interface, and packets received on the interface, in other words inbound packets or ingress packets, are checked against the route map. Packets that match the route map are policy routed, so their next hop is set to 172.16.22.1. And packets that don't match, or packets that are explicitly denied by the route map, are routed normally using the routing table. Note that denied here doesn't mean the packet is dropped. It just means that it isn't policy routed. In other words, it's routed normally. Let's see how this route map fulfills the requirements given a couple of slides ago. First, here is what PBR ACL looks like. A standard ACL matching source IPs in the 10.1.0.0/24 subnet. These are the packets that should be policy routed. So what happens when R2 receives a packet from 10.1.0.1, which is R1's loopback0 interface? Since we have applied the route map to R2G1, R2 checks the route map before looking at the routing table. And the packet matches the ACL referenced by our route map, which permits 10.1.0.0/24. So the packet's next hop should be set to 172.16.22.1. That means the packet will take the route via the firewall. Instead of doing a most specific match lookup in the routing table using the packet's destination IP, R2 decided the packet's next hop based on its source IP, using the route map. Now let's look at another example. This time, R2 receives a packet from 10.1.1.1, R1's loopback1 interface. This time the packet doesn't match the route map. It's not permitted by our ACL, because the source IP is outside of the 10.1.0.0/24 subnet. But that doesn't mean the packet will be dropped. It means that R2 will simply forward it according to the routing table. It does the usual most specific match lookup and finds that R3 at 192.168.23.3 is the next hop. So that's the path the packet takes. Okay, now that we've seen the big picture, let's walk through the 3 PBR configuration steps. Define the target traffic with an ACL, build the route map, and apply it to an interface. Let's start with step 1, defining target traffic with an ACL. The ACL is used to identify traffic for PBR, not to define which packets should be forwarded or dropped. In the CCNA, you saw how to configure an ACL and apply it directly to an interface to permit or drop certain traffic. That's not how we're using the ACL here. In PBR, a permit statement in the ACL means match this traffic. In other words, these packets will be policy routed once our PBR configuration is done. And a deny statement means don't match. These packets will be forwarded normally using the routing table, not dropped. You can use standard ACLs or extended ACLs for PBR. As you know, standard ACLs match only the source IP, whereas extended ACLs can be used for more granular matching, based on source and destination IPs, source and destination port numbers, protocol, etc. For this simple example, I'll use a standard ACL. Here it is. I made a standard ACL named PBR ACL and permitted the 10.1.0.0/24 subnet, R1's loopback0 interface. Here it is. You could also configure a deny statement for the 10.1.1.0/24 subnet, but that's not necessary. Remember, ACLs have an implicit deny at the end. So that's all for step 1, defining the target traffic for PBR. Next is step 2, defining the policy with a route map. Route maps are probably a new concept for you. I won't get into the details, but first let me introduce route maps. A route map is a policy, an ordered list of if traffic matches, then do this statements. Route maps are used in lots of features, not just PBR, such as route redistribution and BGP policy. A route map is made of sequenced entries that are evaluated top-down, like an ACL. Each of these entries has two parts, like we saw before, match and set. The match statements define which packets are affected, often by referencing an ACL. And the set statements define what to do with the match traffic. For PBR, that usually means setting the next hop. The first match wins. The first entry whose match conditions are met is used, and the rest aren't evaluated. This is like how ACLs work. Also like ACLs, route maps use permit and deny entries. A permit entry means the set action should be applied, like setting the next hop. A deny entry means no PBR action should be taken for the packet, so it will be forwarded normally using the routing table. And once again, like ACLs, there is an implicit deny at the end of a route map. So any packet that doesn't match an earlier entry won't use PBR and will be routed normally. The command to create a route map entry is route map, followed by the route map's name, then permit or deny, and then a sequence number. Notice that permit and deny and the sequence number are in square brackets, meaning they are optional. If you omit them, the default is permit with a sequence number of 10. So if you're making a simple route map with only one entry, you can just do route map and the name. Next, configure the match statement. To match an ACL, the command is match IP address, followed by the ACL's name or number. And finally, configure the set statement. To set the next hop, the command is set IP next hop, followed by the next hop IP address. Now let's configure our specific example. First, I created the route map with route map PBR map. Notice that I didn't specify permit or deny or a sequence number. We'll see the effect of that in a bit. Next, I configured a match statement, match IP address PBR ACL. So packets matched by PBR ACL are the ones affected by this policy. Then I configured a set statement, set IP next hop 172.16.22.1. So these packets use the firewall as the next hop. I then confirmed with show route map. Note that the default permit and sequence number 10 were used because I didn't specify them. In this example, we're using a simple single entry route map, so this is fine. Below you can see the match clause matching PBR ACL and the set clause setting the next hop to 172.16.22.1. And that's all for step 2. But a route map on its own doesn't do anything. You still have to apply it to an interface to enable PBR for traffic entering that interface. We'll do that in step 3. Let's finally enable PBR by applying the route map to an interface. In this case, we'll apply it to one of R2's interfaces, because R2 is the router that has to decide to either forward packets toward R3 using normal routing, or to the firewall. Specifically, we'll apply it to R2's G1 interface, the interface that receives the packets from R1. You can apply PBR with the command IP policy route map under the interface. PBR is then evaluated on inbound or ingress packets on that interface. Those terms mean the same thing. It isn't applied to outbound or egress packets. Remember that point. Only packets arriving on that interface are subject to the policy. Packets received by G1, not packets forwarded out of G1. If the packet matches a permit entry in the route map, the set actions are used. And if the packet doesn't match, meaning it's implicitly denied, or if it's explicitly denied, the packet is forwarded normally using the routing table. So here it is, just a single command under the interface. IP policy route map, PBR map. You can confirm with show IP policy. As you can see, the route map PBR map is applied to R2's G1 interface. Now let's verify that it's actually working by sending a couple of trace routes from R1. First, traceroute 10.4.4.4, source 10.1.0.1. This will send a traceroute from R1's loopback 0 interface. This IP matches the ACL referenced by the route map, so it should be policy routed by R2. And here is the output. As you can see, the packet went to R2, then the firewall, then R3 and R4. So it looks like it's working. Next, I'll send a traceroute from 10.1.1.1, R1's loopback 1 interface. This IP isn't matched by the ACL, so PBR won't be applied, and it will be routed normally by R2 using its routing table. Here is the output. This time, the packet goes to R2, directly to R3, and then R4. No policy routing. So these traceroutes show that our PBR configuration is working as intended. R2 forwards packets from 10.1.0.0/24 to the firewall using PBR, and forwards packets from 1.0/24 normally to R3. Let's do one more check to verify, this time with a debug on R2. I used debug IP policy to show debugs related to PBR. Then I sent a single ping from R1, using 10.1.0.1 as the source. Here's the output on R2. You can see the source of 10.1.0.1, and then highlighted in green, it says fib policy match, PBR counted, and then the last line shows it was policy routed to 172.16.22.1. And then I sent another ping from R1 with a source of 10.1.1.1. Here's the debug output on R2. The source is 10.1.1.1, and it says fib policy rejected, no match, normal forwarding. So as you can see, a rejected packet isn't dropped by PBR. It's just forwarded normally using R2's routing table. And now onto the final topic, local PBR. PBR configured on an interface, as we just saw, applies to transit packets. In other words, packets that enter the router on an interface and are forwarded out of another interface. So it doesn't affect packets that the router itself generates. Local PBR applies to packets generated and sent by the router itself, such as pings, traceroutes, or management traffic, letting you policy route those locally sourced packets. So let's try it out with a new set of requirements. First, packets sourced from R2's loopback interface to 10.4.4.0/24 must be sent via the firewall. Here's the loopback configuration with IP address 2.2.2.2. And other packets generated by R2 must be routed normally. Now let's see how to configure it. It's basically the same as before, we just apply it slightly differently. First, I define the ACL to match the traffic. This time I used an extended ACL, since we have to match both the source, 2.2.2.2, and the destination, 10.4.4.0/24. Now let's build the route map. First, create the route map entry, then the match statement, match IP address LPBR ACL, and the set statement, set IP next hop 172.16.22.1. And finally, we have to apply it. Before, we applied the route map to an interface with IP policy route map. To apply a route map for local PBR, the command is IP local policy route map in global config mode. And that's it. The ACL and route map function just like before, but by applying it with the IP local policy route map command, it will now affect packets generated by R2 itself, rather than packets forwarded by R2. And finally, let's verify. First, here's the output of show IP policy now. PBR map is still applied to the G1 interface, but now we have LPBR map used for local PBR. To check that it's working, I sent a traceroute to 10.4.4.4 from 2.2.2.2, R2's loopback interface. As the output shows, the packets took the path via the firewall, as intended. I then did a traceroute specifying 192.168.12.2 as the source, G1's IP address. This time, it was sent straight to R3 and then R4. Note that even though I'm using G1's IP address, the PBR map applied to the G1 interface doesn't take effect. Because the traceroute is generated by R2 itself, interface PBR isn't evaluated, only the local policy is. And since this traffic doesn't match the local policy, it's forwarded normally using R2's routing table. Now let's review the key points from this video. Traditional routing looks up the destination IP address of packets in the routing table to make forwarding decisions. And policy-based routing allows us to override this default behavior using route maps. The first step in configuring PBR is to define which traffic should be policy routed, typically using an ACL, either standard or extended, depending on the requirements. Then configure a route map to define the policy. In other words, what should be done with those packets. Here are the commands we looked at. First, use the route map command to create the route map, use match IP address to specify the ACL to be matched against, and set IP next hop to define the next hop IP address that should be used. Finally, apply the route map to an interface with IP policy route map. Route maps are used in a variety of scenarios, and we just scratched the surface in this video. Here are those points about route maps again. We only used simple single-entry route maps in this video, but when you're doing more complex tasks like defining BGP policies, you'll likely have to use more complex route maps with multiple entries, match statements, and set statements. In PBR, inbound packets are evaluated against the route map, so packets received by the interface on which you enabled PBR. This check happens before the normal destination-based routing table lookup. Packets that match a permit entry in the route map are policy routed, and traffic that doesn't match the route map or is explicitly denied by the route map is routed normally using the routing table. You can also configure local PBR to policy route packets generated and sent by the router itself. The only difference is how you apply the route map, with IP local policy route map in global config mode. Okay, now let's do a short quiz to test your understanding. Here's quiz question 1. Which of the following statements about PBR are true? Select 3. Pause the video now to think about your answers. Okay, the answers are B, E, and F. B is correct because in the context of PBR, denied doesn't mean the packet is dropped. It just means the packet is not policy routed, so it is forwarded normally using the routing table. E is correct because when you apply PBR to an interface with the IP policy route map command, packets received on that interface, in other words inbound or ingress packets, are checked against the route map to determine if they should be policy routed. And F is correct because, as shown here, you can have local PBR and interface PBR applied at the same time. Local PBR affects packets generated by the router itself, and interface PBR affects packets received on that particular interface. A is incorrect because packets that don't match any route map entries are not policy routed. They are routed normally. C is incorrect because local PBR only affects packets generated by the router itself, not packets received on an interface. And D is incorrect because PBR can forward packets based on a variety of things, like source and destination IPs, source and destination ports and protocol, or even the length of the packets, depending on the requirements. Here's quiz question 2. Which command should you use to enable PBR for packets received on an interface? Pause the video now to think about your answer. Okay, the answer is A, IP policy route map, followed by the route map's name. With this command enabled, the router will check packets received on the interface against the route map and policy route them if appropriate. There is no need to use the in keyword at the end of the command, as in option B. C is incorrect because IP access group is the command to apply an ACL to an interface for packet filtering, not to enable PBR. And D is the command to apply local PBR in global config mode, which only affects packets generated by the router itself. Here's quiz question 3. What is the purpose of an ACL in a PBR configuration? Pause the video now to think about your answer. Okay, the answer is C, to match traffic in the route map. In other words, the ACL is used as a traffic identifier. The ACL is not used to define which packet should be forwarded or dropped. That is true if you apply the ACL to an interface with IP access group, but that's not the role of an ACL in policy-based routing, so A is incorrect. B is incorrect because the next hop is specified in the route map using the set IP next hop command, not with an ACL. And D is incorrect because you define the interfaces that should use PBR by configuring IP policy route map on the interface, not by using an ACL. Okay, that's all for the quiz. And that's all for this video on policy-based routing. PBR lets you steer selected traffic along a specific path, giving you more granular control than traditional destination-based routing. The trade-off is administrative overhead, because you have to design and maintain these policies wherever they're needed. This video also might have been your first time seeing route maps. We just scratched the surface, but route maps are a powerful tool used not only for PBR, but also for things like route redistribution and BGP policy control. You'll be using route maps a lot more as you continue your networking journey. I hope this video was helpful. Thanks for watching. Before we wrap up, I want to say a quick thank you to the channel members whose names you see on screen. Your monthly support helps me keep making these videos and keep this content free for everyone on YouTube. I really appreciate it. Thank you for your support. If the video was helpful and you want to support me, click the join button under the video. And please subscribe and like the video. It really helps me grow the channel and keep making these videos for you all. Thanks again.